Hello students. This is lecture number 3 of unit 2 uh, of our course Heat and Mass Transfer. Today we are going to discuss the concept of fin efficiency. In the last class we discussed the uses of fin, application of fins, and why the fins are important in the heat and in the transfer of heat from one body to atmosphere. Okay, now, if a body is heated, sometimes what happens that we apply fins so that the heat can be easily transferred to the atmosphere. So today we are going to discuss this concept of fin efficiency. So, the objectives of today's lecture is to analyze the fin surfaces and to assess how efficiently and effectively the a fin can enhance the heat transfer. The application of fin can enhance the heat transfer from the surface of one, you can say from any equipment or any appliance. As you can see that whenever we compare we calculate efficiency, we most of the time and we first calculate the what is the theoretical possible or what is the maximum possible heat transfer that can happen, and what is the actual heat transfer. Okay, so as you can see in this figure number uh, figure A, that the surface without fins. Okay, this is the surface without fin, and you can see that the root area on which the fin is applied is AB. AB is the cross section of the area on which the fin has to be applied. Okay, so AB is the area which consists of width into thickness. Okay, now you can see in the figure number 2 that when we have applied the fin, and the fin is this one, the extended surface that has been applied, and because of this extended surface the heat will be transferred, the rate of heat transfer from the surface will increase. Okay, so as you can see this is the relationship that is given here. From this relationship it can be calculated that what is the maximum possible heat transfer that can happen because of the application of fins. Okay, so heat transfer that can happen because of the application of this fin is given by this Newton's law of cooling, which is H into A of the fin, area of the fin, the total area of the fin. Okay, as you can see the area of the fin will consist of this surface, the below surface, as well as this surface also. Okay, so all those surfaces from which heat is being transferred because of the convection is the total area of the fin into the temperature difference. Okay, here you can see these are there are two temperature difference. One is the TB. TB is the temperature at the surface of the body. Okay, so the temperature at the surface of the body, and T infinity is the temperature of atmosphere. Okay, the atmospheric temperature, or you can say the ambient temperature. So this is the maximum possible heat transfer that can happen in any in the application when we are applying the fins. This is the maximum possible heat transfer that may take place. Okay, but in actual practice maximum heat transfer is less than this theoretical value. The reason is that here we are taking this temperature. Okay, here we are taking here this temperature is the temperature which is the temperature of the body, but in actual practice the temperature across the fin goes on decreasing. Okay, so so likewise the heat transfer rate also goes on decreasing. So this is the maximum theoretically possible heat transfer that can happen when we apply a fin. Now as you can see this is the actually what happens that this is the ideal case. Okay, ideally the temperature at the surface of the body should be same as the temperature at any place on the fin, but in actual practice what happens that temperature goes on decreasing. The temperature here will be maximum, then here it will be less than 80, then it will further decrease at this point and goes on decreasing till the end. Okay, so that is why the actual heat transfer is less than the theoretical possible heat transfer. Okay, because of the temperature distribution along the fin. So as you can see, this is there is a concept related to fin efficiency is that of zero thermal resistance, okay, or infinite thermal conductivity, or infinite thermal conductivity. This can happen when the temperature at the surface of the fin is uniform and it is equal to the temperature at the base of the fin, or you can see the temperature of the body on which fin has been applied. Okay, so if this happens, then we will get the maximum heat transfer. Okay, this is what I have earlier discussed in the previous slide. Okay, so this is the maximum possible heat transfer that can take place. Okay, now what is the fin efficiency? Okay, let us now define the fin efficiency. As earlier I have discussed that fin efficiency is the ratio of actual heat transfer from the fin upon ideal heat transfer rate from the fin if the entire fin were at the base temperature. Okay, if the temperature at every place of the fin is equal to the base temperature, then this will give us the ideal heat transfer, but actual transfer rate is less than the heat transfer is less than the ideal heat transfer. Okay, so the fin efficiency is basically the ratio of actual heat transfer from the fin upon ideal heat transfer rate from the fin if entire fin so if the fin were at uh, a base temperature. Okay, so this is the ratio that we have got for the fin efficiency. Okay, now let us come to the major part of the of calculating the fin efficiency. Okay, this is the one of the important topics of fin where we calculate the efficiency of the fin. Okay, so as we have seen that this is the maximum possible heat transfer that can be calculated using theoretical formula, and this is actually the theoretical formula that we have got here. And if we multiply this maximum or maximum heat transfer rate from the fin with the fin efficiency, we will get the actual fin efficiency. Okay, now let us write this for each and every case. Okay, for example, for the long fin, if the fin is long, infinitely long, then what will happen that the actual heat transfer that we have earlier calculated will be equal to this value. Okay, under root HPKAC into TB minus T infinity, and this is the theoretical, and this is the theoretical heat transfer, that H into area of the fin into temperature at the base minus temperature of the ambient. Okay, so this is the upper part is the actual heat transfer, lower part is the theoretical heat transfer, that is equal to 1 upon L under root as you can see TB minus T infinity will be cancelled, and area of the fin can be written as uh, area of the fin can be taken as you can say as you can say perimeter into length. So what will happen after solution of this problem, what we get, that we will be getting this kind of equation where 1 upon L under root KAC, okay, KAC this quantity upon HP, okay, KAC upon HP, this is the quantity that we will be getting and it can be further simplified as 1 upon 1 upon m into L, okay, where m is equal to HP upon KAC. Okay, m equal to HP upon KAC under root HP upon KAC. Okay, HP upon KAC under root. Okay, so this is m, this is the value of m. So again for the case of adiabatic tip, when the tip is basically there is no heat transfer from the tip of the fin, so again the ratio will be same, actual upon theoretical, as we have earlier calculated that the fin tip for the adiabatic tip actual heat transfer rate is this one HPKAC or TB minus T infinity into tan alpha L. Okay, tan H sorry, this is m, tan H m into L. okay, upon HF fin into TB minus T infinity. Okay, here it is tan HML. Okay, hyperbolic tan HML due to printing mistake. Here A has been written, but it should be in the place of A, it should be M. Then and that is equal to tan HML upon ML. So as you can see, for the adiabatic fin and for infinitely long fin, this quantity makes the difference. Okay, so rest of the quantities are same, but in case of adiabatic tip, this kind of this hyperbolic function, tan hyperbolic function, come at the top. As you can see, this is the this is the plot for efficiency of straight fins of rectangular, triangular and parabolic profile. Okay, so for three kind of profile, first one is rectangular. Let us find where is the rectangular. This is the rectangular fin and this is the profile. Okay, efficiency profile. Here you can see that on the y-axis efficiency is given, and on the x-axis this quantity is given. Okay, epsilon equal to LC to the power 3 by 2 into H upon KAP to the power 1 by 2. Okay, so this quantity is shown on you can say on x-axis, and as you can see, this profile gives the gives about the efficiency. Actually this quantity tells us about the shape. Okay, this quantity tells us about the shape of the you can say shape factor of the fin. Okay, so as you can see that this is kind of graph we get when we apply or this kind of plot we get when we apply the rectangular type of fin, and when we apply the triangular type. Okay, this is the triangular. Okay, as you can see, this is the triangular triangle. The triangular shape is like this, that this is the straight line also, and this is the straight line. Okay, so this is the triangular shape. Okay, as you can see from here, this is actually this whole part from here to here, from here to here makes a triangular. Okay, triangle. Okay, so at the tip there is only this line. You will say this is the edge, while here you can see some thickness, but here no thickness, only edge of the triangle is visible. Okay, so again you can see this kind of efficiency curve will be getting, and when the shape is a parabolic shape. Okay, like this one, this is the parabolic shape. Okay, so if this kind of shape is there, shape of parabola, then we will be getting this kind of efficiency curve. As you can see, there is not much difference between triangular and parabolic curve. Okay, so parabolic manufacturing a parabolic curve is difficult. Parabolic shape of fin is difficult, so we can opt for the triangular curve. Now as you can see, this is one more shape for the annular fins of constant thickness T. Okay, so this actually tells of us of annular fins, and the thickness is T. Okay, so for a different kind of dimension, as you can see, four different types of dimension, RC, R2C upon R1, outside diameter upon inside diameter. The ratio, as the ratio changes, this is how the efficiency of the fin varies across. Efficiency of the fin varies. Similarly, these are some of the relationship for different kinds of fins, fins to find their efficiency. Okay, so if the shape is of this kind, and straight rectangular shape, the straight rectangular fins, then this relationship will hold. Okay, again you can see this is basically the formula of adiabatic. Okay, when the surface of the tip is you can say uh, surface of the tip surface is sealed. Okay, there is no heat transfer from the tip surface. Okay, then again this is the relationship for the triangular type of fin. As you can see here, the value of m and the value of area of the fin is also given here. Okay, so while calculating the heat transfer rate from the fin, we must utilize these relationship. Okay, we should correctly calculate the area of the fin. Okay, then when the fin is parabolic, then again this kind of shape, this kind of relationship we will get, and these are the other factors that we have to keep in mind, okay, while calculating the area of the fin. Similarly, the circular fins of rectangular profile, as you can see here, this is again the fin is of circular shape, but it has a rectangular profile. So this kind of profile is seen in many application. You will notice that there are in many application where this kind of shape is provided, and for that kind of shape, this is the relationship for the efficiency for the efficiency of the fin. Then again, if let's say pin type of fin, if the shape is like this is the called pin fins, and you can see this is the relationship. Okay, so you can see that only the difference is that the area of fin will be calculated differently. Otherwise, this one is straight line rectangular fin and plane fin of rectangular profile have the same relationship, but only the difference is how the LC and effective length and area of the fin is calculated. Okay, so further, these are a few more relationships that we have to keep in mind while calculating. You don't need to remember all those relationships. You only have to understand what these relationships are and how their areas, especially this value, this area and this value m is calculated. Okay, for each case, you can see that things change quite a lot. So you have to look at the profile and you have to find the values, and then you have to calculate these values. Then again, for the pin fin of parabolic shape, okay, this is the parabolic shape of fin, and this is the efficiency of the uh, fin of parabolic profile. Okay, then pin type of fin of parabolic profile, blunt tip. Okay, the tip is little bit blunted, tip is a little bit cut. Okay, so it will give a shape of you can say this kind of shape. Okay, so you can see that this is the relationship that holds for the parabolic blunt type of chip. So these are some of the important points that you must remember while dealing with the chip efficiency. First thing is that the fins with rectangular and parabolic profile contain less material and are more efficient than the ones with rectangular profile. Okay, so as you can see that since it has less material, so they are able to transfer heat at a faster rate. Okay, so that is why they are more efficient than the rectangular shape of fin shape. Okay, so that is why parabolic and triangular shape is preferred over other shape. Then again, the fin efficiency decreases with increasing fin length. Okay, as we increase the length of the fin, the efficiency, as you can see that it is a ratio of actual versus ideal. So ideal, the ideal heat transfer rate increases, and this actually results in the decrease in the fin efficiency. Similarly, the increasing of the length beyond a certain value cannot be justified unless the added benefit outweighed the added cost. Okay, this is the things, these two things that you have to keep in mind, that if we are applying a very high length of fin, then we have to also look at the cost. Okay, if the cost, we have to keep a balance of cost versus benefit. Then fin length that causes the efficiency to drop below 60% usually cannot be justified economically. Okay, so if the efficiency is more than 60%, then we can increase the length. Okay, but as soon as the length of the fin decreases below the 60%, then it cannot be justified economically. Okay, economy of the fin, application of the fin cannot be justified. Then we have to look for the other methods of heat transfer. Okay, similarly, efficiency of the most fin used in practice is above 90%. Okay, this is the important thing that you should remember. Okay, we mostly we use the efficiency of the fin which is more than 90%. So this is what we today we learned. We learned how to calculate the fin efficiency and what is the meaning of fin efficiency. Then we calculated the effective fin efficiency for these two type of cases, for the long fin and for the adiabatic tip. When the you can see the tip of the fin is insulated. Okay, no heat transfer from the tip of the fin. So these are some of the review questions that you should go through, and the questions are that like this: that what is the reason for widespread use of fins on the surfaces? You can easily answer this question if you have gone through this course. And then what is the difference between the fin effectiveness and fin efficiency? We have studied effectiveness as well as efficiency, so you can again answer these questions. Then the third question is: fin attached to a surface are determined to have an effectiveness of 0.09. So what do you think the rate of heat transfer from the surface has increased or decreased at the addition of these fins? Okay, so this is actually the question related to the effectiveness, as you have earlier studied this effectiveness thing. So, and we have also studied the efficiency. So you have to justify whether adding the you can say by after addition of the fins, whether it has resulted in any benefit or not. Okay, so these are the references. As you can see, this is the very famous book, and this is the book from where I have made the PPT, and these are other two books from where you can also refer, and I have also referred for the guidance while preparing this lecture. So thank you for all. Tomorrow we will be discussing, will come with a new topic of heat and mass transfer.